So we first talked about variables, just explaining what variables are, and in general. So remember, we have our explanatory variables and our response variables. Our explanatory variables are going to be those that are independent because they are explaining our response. So we want to make sure that those kind of stay constant and don't aren't affected by anything in order for them to make sense. So yeah, we have our explanatory variable, and then we have our response variable, which is dependent upon that explanatory variable. So it does change depending on what happens to the explanatory variable. That response variable will change. And then remember, there's something called a confounding variable, and that's basically a third variable that is going to affect our data that we weren't planning on looking at. So this is going to be something that we don't want because it could skew our data and give us unrepresentative data in the end. And then treatment goes along with randomized experiments, which we'll go into for the at the next slide. But treatment, just remember, is something that we do to the variables when we're doing a randomized experiment. Okay, and then so other types of variables, other ways to classify them can be between categorical and quantitative. So categorical just means that they there's some sort of category to them, that they're labels, groups, things like flavors, brands of something, colors. And then the two different types are nominal and ordinal. Nominal variables mean that there is no type of order to the categories. So things like flavors of something, there's no order to those. And then ordinal does have a hierarchy. So those are things like class standings, so like freshman, sophomore, junior, senior. That would be an ordinal categorical variable. And then our quantitative variable is going to be variables that involve values to them. So they are numbers, and they have consistent intervals in the way that numbers always do have that. And then we have discrete and continuous quantitative variables. So discrete means that they are, that's all, it's specifically just discrete variables. There's, they can only take on a set number of values, while continuous can take on any amount of values there. It doesn't matter. These are things like weight. Any type of measurement is usually a continuous variable there. Okay, so some things when we're taking samples of these variables, some issues that we can have. So first is just our low response bias, which is something that we can't necessarily control. It just means that we put out, some sort of survey or whatnot, and not a lot of people respond to it. So it's not going to be as representative of our population there. Non-response just means that people aren't responding, and maybe those people are the ones that are representative of the population. So it's similar to low response, so this is basically saying that the people who, maybe aren't as interested in the topic aren't responding. So that's going to change the idea there, that it's going to give you different data than what we're looking for. And then question wording issues are basically just talking about how you word your question that you're asking your participants and how that can kind of lead them one way or another. So using different things, so there's things like the importance of the order. So, the way that you order the different options can affect that. If you use words that are really powerful, like prohibited, instead of like not allowed, it kind of will make people want to go against it because people don't want to be told what to do. So if you use strong words like that, it is probably going to be that could change some problems there. So there's plenty of issues that can happen with question wording, but the main idea is that how you ask your research question to your participants is important because it can change the way that they answer it in the end. Okay, and so experimental and observational studies. So these are just different types of studies, and they're dependent on if we're either going to be affecting the participants or not. So for experimental studies, basically what's happening, like what I talked about before, is that we're going to have some sort of treatment on our on the different participants or the variables. So the researcher will be changing something about the different people or whatever the variables are in the groups. And we also call it a scientific study. If you think about, in science, you're usually doing something to change something. So yeah, that's how you assign groups. you do it randomized, which is going to give you a more representative sample, because then you're less likely to have any sort of bias with it. So if we go to observational studies, this means that the researcher isn't going to put any type of manipulation on the data. They're just going to kind of watch things that happen. I liken it to like people watching. You just kind of see what's going on, and you take data upon it, but you aren't making any sort of change to the data, or you're not making any sort of change to the variables that you're looking at. So yeah, that's general what it is. Observational studies can cause a problem because, remember, confounding variables, those are something that can happen in observational studies because we're not controlling for it by randomizing our experiments. So if we want to control for those confounding variables, we would rather do an experimental study in order to do that there. All right, so let's do a review question here. So this one says that in a survey of military veterans, the variable of branch of service, Army, Navy, Marines, Coast Guard, etc., is what? So read through these options and then let me know what you think, and then we will discuss it together. Great job. Absolutely. Good job. So this answer would be A here, because we are talking about a categorical variable, because these are different categories. They don't have values associated with them. They're different groups. And then if we do want to get specific, this is actually a nominal categorical variable, because in theory, they don't have any sort of hierarchy to them. So we're going to call that a categorical variable that is also nominal there. So our answer is A there. So great job. All right. All right, so another thing that we talk about when we're taking samples is reliability. So this is discussing in terms of consistency. So if we take a bunch of samples, are they consistent between one another, which is what we want, because that's showing that we're getting representative samples. So and one thing to keep in mind, that we do always want to have a large sample size to keep that representative idea. So if we do have a small sample size, we're going to have a lower reliability because they're not going to be as consistent between the groups. There's a higher chance of making them unreliable. And then our margin of error, that's the equation for it, our 1 divided by the square root of our sample size. And it kind of makes sense that it has an inverse relationship with sample size, because the sample size is being divided, there's 1 divided by it. So that means that they are inversely related. And the margin of error is just discussing the difference between our sample percent and then the true population percent. So our population, the fixed one, and then our sample. So the difference between those. And we think that it's going to be between the margin of error at least 95% of the time. So that's how we interpret what the margin of error actually means. And then obviously this equation is how we find the actual value of it in terms of, our reliability. All right, let's try this review question. So a random sample of 1,000 residents in Montana, which has a population of 1 million, is taken to estimate the percentage of adults that of that state who do not have cell phone service. A similar survey of 1,000 adult residents is conducted using the same methodology in California with a population of 39 million. Comparing the 2 polls, we would find out what. So read through these options, let me know which one you think is correct, and then we will go over it together. All right, all great answers. So, so let's look at this one. So remember, our margin of error is not affected by our population size because our margin of error is affected by our sample size. So, so if we read through these, we have the fact that, so our margin of error for A, it says the margin of error of the California poll will be greater than the margin of error for the Montana poll. So that's not true because we can't say that in terms of the population. That's not what we're looking at. So that would be if we're trying to discuss, the size of that we have a bigger population for California than Montana. So that's not correct. And then for B, the margin of error for the California poll would be less than the margin of error for the Montana poll. This is also not correct because we do not, this doesn't matter once again because we're not looking at population. That doesn't affect it. We don't have the data for that our sample, so that B is not correct. So our answer is C because we're going to say that our margin error is about the same because we do have a random sample of 1,000 adults in each one. So dependent on our sample size is how we decide about our margin of error. So our sample size in both of them is 1,000. So that's what we want to look at in terms of it. So since these are the same, that means that we can assume that our margin of error is going to be about the same in that case because we do have the same sample size there. So it doesn't have to do with the population size. That's why we want to make sure that our margin of error is has the relationship with our sample size, not our population. So just to keep in mind. Does that make sense to everybody how we did that one? All right, awesome. All right, and like I said, feel free to ask any questions throughout. Please let me know if something doesn't make sense. I'd be more than happy to explain it. This review is for you guys, so I want to make sure you guys have a good grasp on all the information. So let's talk about non-probability sampling. So this means that basically there's not a probability for each sample that we take out because they're kind of we just take them based upon what we have or, who responds back. So for volunteer samples, we say the sample chooses itself because it's whoever decides to volunteer there, whoever decides to involve themselves in the sample. And convenience samples just means whatever's easiest, whatever sample you have access to, that's going to be your convenience sample. And then the idea of this is that human choice isn't random selection, so non-probability sampling isn't that good. It isn't going to give you a representative data set, so we do have a higher chance of bias there. And remember when we talked about observational studies, this is similar in the fact that if we do an observational study, we're not affecting anything in any way. We're just kind of choosing whatever's easiest there, whoever responds. And that's why for observational studies, if we're not imposing any sort of change, we cannot make any sort of relative conclusions there. Yep. Okay. Here's another question. So true or false, since the nature of the population does not matter, the sampling distribution of a sample proportion will approximately follow a normal distribution even for a convenience sample. So try this one out and then let me know what you think. Yes, great job. We got some English, we got some Spanish in there. I like it. I'm a speech pathology major, so A+. So our answer here is false. So when we are talking about our normal approximation, remember, and so this one we're talking about a convenience sample that's a part of this question, and that's not true. The sampling distribution, we can't assume that it's normal if we have a convenience sample, because remember, our convenience sample is just kind of whatever we have, and that's not always going to be normally distributed. We want to have a randomized experiment in order to try to make that assumption that our sampling distribution is going to follow a normal curve. So So yeah, this one is false because convenience sampling does not represent that. So great job. Okay, so we're going to talk about, I don't know what I'm doing. We're going to talk about data displays for measurement data. So remember, this is the same thing as when we talk about quantitative data. So measurement data displays, same idea. So quantitative data, quantitative, I don't major in spelling. So the different ones that we talked about definitely were our histograms and dot plots. So remember, histograms are usually used for larger data sets because, you know, we can have really any amount in these bars and we can represent it in a smaller space, while on the dot plot, each sample is represented by a dot, so we couldn't like have a million of these in here, when theoretically we could do that on a histogram as long as our scale is able to show that there. So yeah, that's really all these are. It's showing you the frequency of each quantitative variable on your x-axis there, showing you the frequency of it. And then you're able to compare, you know, the heights of these to see, you know, the difference between them. So those are quantitative data displays there. Okay. I'm sorry, I'm probably going to give you motion sickness. So when we're talking about quantitative data, we do often describe it in terms of the shape. So if our mean equals our median, and that also equals our mode, we are going to be discussing that in terms of being symmetrical, because that means that all of our measures are going to be, all of like our main measures are going to be equal to each other. So that's where we're going to get it to be symmetrical. A left skew looks like this. You can't really see that. Hold on. Our left skew is going to be when the values are more spread out on the left side. So our mean is going to be our lowest. So your mean is always going to be the lowest on wherever the spread is. And then our median is always going to be our middle. And then our mode, remember, that's our most commonly occurring value. So that makes sense that it's at the same place of the highest value on this skew. So that's how we write that. When in comparison for our right skew, our mode is going to be the lowest because that's where the highest value is here. And then our mean is going to be the highest because it's more spread out on the right side. And then, like I said, the median is always the center value there. So that's just different ways that we do describe the shape of our data. Okay, I don't know what, I'm struggling. All right, so let's try out this question. So the director of admissions in a small college administered a newly designed entrance test to 100 students selected at random from the upcoming freshman class. The purpose of the study was to determine whether students' grade point average at the end of the freshman year can be predicted from the entrance test score. So at the end of the year, when all the data are available, what would be the graph you should use to display this data? So based on what we just talked about, try this one out and we will go over it together. Okay, great. Good answers. You guys definitely have a grasp on the types of graphs that we would use for quantitative data. So as we can see, our GPA is going to be quantitative data. So that means that, you know, we could use a histogram or a scatter plot, but since they're trying to find the relationship between these admissions tests for the GPA and then their entrance test score, if we're looking for the relationship, we do want to use a scatter plot, because remember, scatter plots are going to be talking about two quantitative variables. So if we're talking about two quantitative variables, we are going to use a scatter plot, which that's why it wouldn't be A or B. And then we want to remember when we have a graph, our explanatory variable is going to be on our x-axis, and then our response variable on our y. So if we look at this, we're trying to figure out if the student's GPA predicts the entrance test score. So GPA, predict, entrance score. So if you ever see predict, you can always assume that this is going to be explanatory first and then response, because we're seeing if this first one explains our second one. So GPA is going to be on our y-axis because it's trying to, we're seeing if it explains that. So you want to see the relationship between the two, and then you want the response on the y-axis there. So yeah, so that's why we would have letter C for the answer there, because we want we would want our scatter plot with the entrance test scores on the y, because that's what our response variable is. We're seeing if their GPA affects that or shows that. So, and then our GPA on X, because that's what's explaining it there. So response on the y-axis. So yeah, all right, good job, guys. All right. Okay, so 5-number summary. This is what we use when we're talking about, it's a good way to summarize our data and, you know, the main parts of our data. So we do have our minimum, our maximum, and then the different quartiles. You'll often see this drawn out in a box plot. So if we were to draw a sample box plot here and to label it, we're going to have our minimum down here all the way to the left, our maximum up to the right, and then we have our different quartiles, so Q1, Q2, also our median, and then Q3. And like I said, our Q2 is also our median. And then if we're looking at in terms of having percentiles, this is going to be our 25th percentile, 50th, and then 75th percentile. So those are our different parts of our 5-number summary. And then our interquartile range. So our range in general is just our maximum minus our minimum. So that's showing you that entire range on that box plot. But our interquartile range is exactly what it sounds like. It's the range between, within your quartiles. So it's technically showing you the range within here. So you just do your Q3 minus your Q1 in order to get that IQR here. So that's a good way to describe our data and summarize it there. All right, so our standard scores are basically when we get a sample and we find all the data about it, we want to standardize it so that we can make conclusion based upon things like the empirical rule and what we know about a normal curve and the percent of the data between them. So our standard scores are just showing your observation in relation to other observations, and the way to find it in terms of an equation we just have, so we call our standard score Z. So Z is equal to our value, so like our sample value, minus our mean, and then we're going to divide that by our standard deviation. So in the case if we have let's say that we had a mean of like 6, and then, so I'll write this mean of 6, and then we have a standard deviation of 2. That means that one standard deviation away is going to be equal to 8, because we're going to add 2 here. So that would correlate with our standard curve of having our mean at, for a standard curve, our mean is always going to be 0, and then our standard deviation is going to be 1. So this 8 is going to correspond with one standard deviation over, so that's going to be 1 on this normal curve. So for this one, our value of 8 is going to have a standard score of 1, because 8 is one standard deviation away from the mean for our what we have already for our sample. And then if we standardize it, it's going to correspond with the value of 1 there. If you see, from on this value here. So that's where we get that from. Okay, and like I said, the empirical rule is something we often look at in terms of talking about the percent of the data within different standard deviations. So we have our empirical rule talking about the percent of the data within these different within these different types of our standard deviations. So for example, when we talked about confidence intervals, remember we often use a 95% confidence interval. And the reason why our multiplier was 2, because we would say that 95% of the data lies between plus or minus 2 standard deviations. So this is like when we would have our lower bound at the end of our confidence intervals, and then our upper bound. So we have this, and then this is going to be representing 95% of our data between these values here. And then same with 68 and 99.7, but just between 1 and then 3 standard deviations there. So our empirical rule is basically showing us a standardized normal curve like I showed you for standard scores, but it's showing us, the percent of the data between these different amounts of standard deviations. Okay, so when we're talking about different studies, case control studies, this means that we're talking about what the study is looking at. Is it looking at things that are going to happen in the future or things that have already happened in the past? So people with a response of interest from a group of cases, and then they're compared to a group of controls. So things that are happening versus a group that nothing is happening on, they're your controls. And that's the only difference, is the cases have they have the response and the controls don't. And then this is for, and so that means that the type of study is very common in the factors that you might associate it with, like uncommon diseases in that case, because our control is going to be, the people who don't have it, and then those that do have it. So that's something that we often use in this case control studies in general. So in a retrospective study, we're going to be comparing people, once again, who have the condition, the response variable, and those who don't, which is your control. And so we compare the patients who have the disease today to those who don't have it, and then ask them about past exposure. So retrospective is talking about in the past. So that's something to note there. So retrospective is talking about the past, while prospective is looking at in the future. We're trying to figure out what we think is going to happen. We follow them over time, kind of like a longitudinal study. We find the people with different types of behaviors and exposures, and then we follow them over time to see how many end up getting that response variable. So we don't look at people at the same time and then, in the past exposures and their behaviors. We're looking at people who currently have these exposures and behaviors, and then figure out what the outcome is in the end after we follow them over a certain amount of time there. All right, so correlation is when we were talking about basically the relationship between values. And so it is going to be a number that indicates basically how close our values are together on the line. So when you see all the dots and then on your graph, and then you'll have like a straight line going through it, we want to see how close all the dots would be to that straight line to see what the correlation of them would be. So, and we call it the strength plus direction because it is talking, that's what it's discussing. The strength is going to be our value between negative, or technically between 0 and 1, and then our direction is if it's negative or positive. So technically they're not values because our negative or positive is just showing us our direction. And yeah, just as the premise that correlation of 0 shows there's no relationship going on. Correlation of 1 shows a perfect positive linear relationship, and then a correlation of -1 shows a perfect positive. -1 is a perfect negative linear relationship there. So yeah, just finding that relationship between two quantitative variables for correlation. So we are talking about quantitative and measurement variables here. All right, so an equation of a line, we kind of talked about this in terms of our correlation, that we would have a line going through our data. So our equation of a line is just showing us, excuse me, this is like how we would find it. And if we just kind of draw this out to see, for it to make sense in context. So A is going to be our y-intercept. So this is our y-intercept, so where it intersects the y-axis. And then B is going to be our slope, so our rise over run, whatever this slope is. So this is going to be B. And then X is going to be whatever value you're choosing on the x-axis to find the value on the line there. So So yeah, that's all that is when you're making an equation of a line in order to find that. So yeah. Okay, and we just talked about correlation, but we want to just talk about things that could, some issues that can have if we're talking about correlation and regression, things that we don't want to do. So first of all, you want to make sure that it is linear in order to use correlation. If it's not linear, then we can't use that and won't make sense. And also, if we have outliers, that can also skew our data and it won't be as representative there. Then also keep in mind that correlation does not equal causation. So that means that if something's correlated, doesn't mean that it causes it, but it's saying that we have evidence that it's there is some sort of relationship there. And then extrapolation is the idea that, you know, we have our data set and we have our regression equation and the values there, that we have our observations and then our predictive values on the line. And extrapolation is basically saying that we look way down the road for data sets that we don't have, you know, in the future, and try to make some sort of like predicting those values just because they fall on the line and follow the same pattern, which is not true, because we can't make the assumption that the same data or that the same trend is followed as we go further out in the data. So we're only allowed to make inferences about the data set that we have currently. We can't make inferences about those that are farther out, because that's extrapolating and making different assumptions there. And illogically interpreting your y-intercept is basically saying that just because what does that mean? Sorry, just because your y-intercept is shown, it's going to be shown, you know, on your line, doesn't mean that it is, you know, actually something logical. So if you have, you know, time on your y-axis and you're just looking at like the increase of time and your y-intercept is, you know, negative, that doesn't make sense, because you can't technically have negative time if you're talking about it in that way. So that would be illogically interpreting your y-intercept, because a lot of samples don't have x equals 0 because that's not what you're looking at. So we're often looking at the data above that. So we don't always want to look at the y-intercept and make inferences about it. All right, so here's a question here. So we have, so true or false, for all the books in the Library of Congress, correlation between the thickness of the books in inches and their number of pages would be positive. So let me know what you guys think the answer for this one is, and then we will review it together. Great job, absolutely. So our answer here is going to be true, because this is showing that basically as the thickness of the pages increase, so as the inches increase, that's also going to mean that there's an increase in the number of pages. That just makes sense. So that means that we are going to have a positive relationship, because if we have inches here and then pages, well, actually, we'd probably have pages on our x and then inches. That means that, you know, as our pages increase, so as these go higher, the inches are also going to go higher. So we are going to have that positive relationship there. All right. Okay, so risk and odds. This is when we're talking about probability. So risk is just talking about, in general, the likelihood of an event happening, but they do have different interpretations there. So our risk is going to be basically the likelihood of an event happening in general, and the way we find it is going to be our number with the outcome, and then our total number of outcomes in general. And then risk is probability that it will occur, once again. And then our odds, the only difference there is that we're talking about the odds of it happening versus not happening. So that's the only difference between the two. They're both talking about the likelihood of something happening, but we do want to make sure for odds we're also comparing it to not happening there. Okay, so risk between groups or situations. So our relative risk is saying that we have the risk of one group and then divided by the risk of the other group. So that's showing the relationship between them. So the group one is how many more times likely to experience the event than group two. So we are comparing groups here and then saying, you know, how much one is more likely or less likely to experience the event. And then increased risk is exactly what it sounds like. You have relative risk. So, you know, how many more times it likely it is to experience the event than group two. And then we want to talk about how much actually higher it is. So we're saying, you know, how many times more likely it is, but then we're finding out specifically how many more times higher it is with increased risk. So how do you know which group to divide for? Good question. So you want to use and often it'll tell you know group one and group two, but if it, you know, the question will say, you know, the risk of females getting you know, heart cancer is how many more times likely than males getting heart, you know, something like that. So it'll be something that's that makes sense. It'll say that in there, that it's finding out, you know, it's between one or the other. And technically, you know, you could, if you switch it around, it would be like they're this many times less likely. And you can also kind of understand that by seeing, you know, how many, you know, if there's more, a higher chance in the risk of the first group, or the higher chance one, the one that has the higher chance is going to be your first one. And then the second one is the lower chance is going to be your second one that you're dividing by, because the common thing is that we say that group one is how many times more likely. So it's going to be that higher one there. So yeah, that's what we found there. Does that make sense? Okay, cool. All right. So probability rules. We have 5 probability rules that we use all the time. So probabilities do have to be between 0 and 1. They have to be some sort of decimal between there. 0 means it's not going to happen at all. 1 means that it's definitely going to happen. It's a certain event. And then our second rule is that if you have probabilities that can't happen at the same time, then you can add them together to say the probability that at least one of them occurs. So for example, the chance that it rains in State College, and then the chance that it snows, which is definitely not true because it can happen at the same time. But think that those can't happen at the same time. If we want to find the chance that it rains or snows, we can add them together in that case to find the probability that at least one of them is going to occur there. So our third one is going to be 1 minus the chance of the opposite thing, which sounds a little weird, but it's basically saying that if you're trying to find the chance of something, whatever the opposite of that is going to be, it's just 1 minus the chance of the opposite thing, because you know, it all has to add up to 1, remember, in the end. So if the chance of something is 0.8, then that means that the opposite thing is going to be 1 minus 0.2, because the opposite thing is obviously going to be 0.2 because they both have to add up to being 1. So that's how we find it, and that's why we start with 1 minus. Our fourth one is that if they're independent events and we want to find the probability of all their chances together, we just multiply them. So similar to 2, but that's talking about or. And then number 4 is talking about and. And then our fifth probability rule is, so if the ways that one event happened are the subset of the ways that a second event can happen, the first event can't have a higher probability, because that means that they have to happen before the second event can happen. So they can't have a higher probability because the second event relies upon that. So that's gonna have a higher one there in that case. So that is our fifth rule there. So let's try this one. So true or false, when you flip a thumbtack into the air, can land point up or point down? So true or false, since they're just 2 possibilities, the chance of each one must be 50%. So let me know what you think the answer to this one is. Great job. You guys are killing it. Absolutely. So our answer to this one is false. Not to be tricked up because the fact that it's right, exactly. It's because the thumbtack, on the higher side is obviously, that's going to have, this is supposed to be a thumbtack, looks like an acorn, but this is going to have, less weight. So it's going to have a lesser chance of being able to, is going to fall on that. It's probably not going to fall on the tip there. So that's why it's not going to be 50-50 in that case, because that would be assuming that they weigh the same in that case. So that is false. So great thinking. Absolutely. All right. Oops. Okay, so expected value is something that we use when we're talking about, if we were to take a bunch of samples over and over and over again, what do we think the average of all those samples would be? So we call it the long run average of that. So that value of the measurement, like I said, if you repeat the process over and over again, so you basically take the sum of all your values and then times their probabilities and add them all together, because you're trying to figure out, the probability of that value happening, and then add that to the probability of the next event happening, and then add them all together to find that long run average of what we think it would be over time, so what we expect it to be. Okay, and the law of large numbers is basically saying that if we have more trials over and over again, that the averages or proportions are going to be more stable, but the sums or the counts are going to be more variable, because the more that we take, we're going to have different sums for each of them. But overall, the averages are going to be more stable because we're taking so many. Remember, we always want to have a large sample size. So if we have a large sample size, that means that that we're going to have a more stable average there. But then the sums are going to be more variable, because those are going to go dependent on, those are going to be more variable in terms of that. But so yeah, and then this doesn't happen because of this does not happen by compensation for bad luck. So this means that since these events are independent, since these trials are independent, that means that when one happens, it doesn't affect the next one, and that's what it means by it doesn't have memory. So it doesn't mean that, if you had a bad run of luck but then a good run of luck in your samples, that they like even out. So that's why we would have more variability in that. So, all right. And then, so our normal approximation method. So that means that if we have large random samples, like I was talking about, you always want to have larger samples. Then they're going to be more representative of the population. And then this quote here is literally just saying the same thing, and the fact that, if we have a large number of the trials, it's going to be approximately normal and definitely, more representative of our population value there. And then these are just the equations you use to find the standard deviation of either a sample mean or a sample proportion. And this is saying, we show that they're equal to our population standard deviations, because if they are, if we take enough samples, we're going to assume that it's going to be representative of the population, so we can use those same equations there in that case. All right, and then, so confidence interval steps, these are the 4 steps we take to get a confidence interval. So our first step, we want to figure out what's our parameter of the statistic that we're looking at, that we're trying to find. So then our step 2 is figuring out, can we apply normal approximation? So you want to figure out if it's a random sample. So remember, like in experiments, we want to have a random sample, not an observational sample, for it to be representative. And then we do also want to have a large enough sample there. And then our third step, estimate that standard deviation, which, like I said before, we can use if these first 2 steps are correct, or if our second step, those assumptions are met, then we can use the population standard deviation to assume that the sample statistic is approximately the same as that. And then our fourth step is going to be computing that statistic and then multiplying it by z star, and then times our standard error there. So yes, that's a rule that we often use, is that 30 or greater. But often it'll be larger than that. But that's a good rule of thumb to use, that it's at least 30 or greater. That kind of goes towards the central limit theorem there. But that's a great question. just, because it's not subjective there. Okay, so a question about confidence intervals. So true or false, everything else being equal, a confidence interval for an average will be shorter if the sample size is much larger. So try this one out and we will go over it again. Okay, so let's look at the correlation between sample size and our standard error. So remember, our standard error is telling us kind of our spread. So if we have our confidence interval and we're looking at our standard error, the higher that our standard error is, the wider it's going to be. If our standard error is bigger, then it's going to be a wider confidence interval. So if we have a smaller sample size, that means we're going to have a larger standard error because remember, we want a big sample size to decrease that error. But then a smaller sample size is going to be a larger standard error. And in this case, it's saying, so if the sample size is much larger, so this is saying that our sample size is increasing, which means that our standard error is going to decrease. So that means that the interval is going to be shorter because we do have a smaller standard error. So it's going to decrease there because that standard error is going to bring it in a little bit. So does that one make sense? So that's true to recap. Yes, the standard error is showing the width of the confidence interval because that's our spread. Standard error is your standard deviation of your confidence interval. So it's the same thing as your spread and the variance. So if you have let me draw. So if you had like a short standard error, let's say our standard error was 2. So that means that from our, we're going to say let's just say that the spread would be 2 from our, so -2 and then +2 from our, our initial point estimate, but then our standard error is going to be like 7 for this one. And so our initial and then +7. And this is going to be a larger standard error, which we get from having a smaller sample size. A smaller sample size is going to give us that larger standard error because if we have a smaller sample size, we're more likely to get an error. So we're going to give more leeway in that case. So larger sample size equals smaller standard error, which also equals a more narrow confidence interval. Narrow. Does that make sense? It's the same as the confidence interval, but it's the same as the width of the confidence interval, if that makes sense. All right, cool. Great questions. All right. So here's another question. So random sample of 100 college students found that they got an average of 6 hours of sleep the night before their last midterm with a standard deviation of 2 hours. This says that a 95% confidence interval for average hours of sleep for all students before a midterm is going to be what? So see what you think about this one and let me know which confidence interval you think it is. Okay, good. Yeah, so you guys are definitely on the right track. So here our average from the sample is going to be, so this is our point estimate, is going to be 6 hours. So this is our X bar, which is going to be 6 hours. So we can start with that. So 6 hours and then plus or minus, but remember we do have to take it in to affect our multiplier. So for a 95% confidence interval, our multiplier is going to be 2, and then times our standard error, which, well, let me actually write the value. So times our standard error, which is 2. So that's why the answer would be B, because you want to make sure that you multiply the 2. So you have our point estimate, and then plus or minus our multiplier, and then times our standard error. So you just want to make sure you use all of that in there. Remember, a multiplier is dependent on, what our percent confidence interval is. So then it's 2 for 95%. So cool. That makes sense to everybody? I definitely understand what you said too. But remember, if we're talking about margin of error, if it said that the margin of error was 2 hours, it would be A, because our margin of error is this, right side of all the equations is our margin of error. But since we're talking about standard error, we do have to make sure we still multiply that by our multiplier there, obviously. Okay, so hypothesis testing, this was kind of the last thing we talked about. First, you want to figure out, our first step of hypothesis testing is trying to figure out what our parameter of interest is, just like we did in confidence intervals. So mean or proportion, categorical or quantitative data. And then you want to write your null and alternative hypothesis. So your null is showing that there's no change. Alternative is saying there's some sort of change going on. And then our second step is going to be asking if what's the sample statistic, and then do we think that the distribution, so we always assume that the null is true. So what is the sample statistic, and then what does that distribution look like if the null is true? And then if we find out, remember, we always want to have it be normally distributed to find this out. So if it's normally distributed, go ahead and calculate that standard score. And then dependent on that standard score, we try to figure out, how likely is what we got something that would happen. So then you find a p-value based upon that standard score to figure out that probability of how likely it is that, what happened is actually true. And then the last step is that you're figuring out what you conclude in that. So what do you conclude about your p-value? So what does this even mean in general? So that's encompassing all the first 3 steps there. All right, so here's a question. So, and 1 minus p. You mean like, I guess 1 minus p would be showing you the percent of the data that's supporting that it's correct. So you want a large percent there. The p-value is going to be, you want that to be small, because the p-value is saying that's like the probability that it was just by chance that you made a mistake. In reality, there's not actually a difference. So you want that to be small, because the 1 minus p is going to show you the other part of your graph that's basically saying the probability that it wasn't by chance and that what you got is correct. So that makes sense. All right, awesome. Good question. Oop. Okay, so let's try this question. So true or false, p-value is the probability that our null hypothesis is correct. So this is like interpreting what a p-value actually is. So try this one out and let me know what you think. Okay, so remember, let's review what we conclude from our p-value. So when our p-value is less than alpha, so we're saying that it's small, then this means that we're going to reject the null. And then if our p-value is greater than our alpha, that's the probability that it's greater than alpha, showing that we think that it could be by chance. That means that we're going to fail to reject the null. So we always assume the p-value is calculating assuming that the null is true. So it's not necessarily a probability that the null is true, because we already make this assumption, so there's not a probability of it. So it's the probability of the fact that we could be wrong, basically the fact that it could have been just by chance. So, if I have a curve here and I get, a p-value based upon like our test statistic, and then my p-value is down here, this is basically saying that this is the probability that what we got happened by chance, which we don't want. We want it to be because there's actually a change in the population. So that's actually what the p-value is representing. So this one's a little bit different because it sounds like it's trying to do one or the other, but it's basically just saying this isn't the definition of a p-value. It is a probability, but it's not saying that the null is correct, because if our p-value is smaller, that means that we're going to reject it and whatnot. So that doesn't really make sense. So the actual definition of it is going to be the probability that it happened by chance. So that's why we want it to be small, because we want to say that we don't think it happened by chance. We're more concerned, and this would be the 1 minus the p-value that you were talking about. It is, I know, trick question. But yeah, it's just kind of discussing the fact that this isn't the definition of what a p-value is, because you basically always assume that the null is correct. So it's kind of like the probability is always like technically 100, but so yeah, does that make sense to everybody? I'm losing my voice. Too much stat this week. Okay, awesome. So one more thing to talk about. Okay, so when we're talking about these things that could be happening when we have hypothesis tests, these are just different cautions you want to keep in mind. So when we have a large sample, and then we find statistical significance based upon our p-value, we want to keep in mind that they may not be practically significant. Maybe we took all these values, but they're not actually practically significant. They're just it was just shown kind of in the numbers. But so that's why we want to look at practical significance to see if this is something that's actually applicable in the real world or not. And then a small sample caution is saying that, even though it's showing it's not significant, it's like the opposite of the first one. So it's showing that it's not significant statistically, that it actually may be significant practically. So even though we didn't find statistical significance, it actually may be significant in real life, so practically. And then multiple testing caution, is basically saying that if we have a large number of significance tests conducted, that may mean that some individual tests were deemed significant just by chance, if we're doing a bunch of samples and a bunch of tests. So that can give us some false positive results, saying that we think that there's a change when there actually isn't. So we thought that there was significance, but there's not. So that's the issue with doing multiple testing, that, some of them may not actually be representative there. So, all right, this is the end, RIP. So how do we know that it's not? How do we know it's not multiple testing causation? Oh, like how do you know? Yeah, okay, so it's basically saying that you have tests that are showing that it's like overall it says, okay, this is statistically significant, but you were doing a bunch of tests, and sometimes those tests, since they're it's only one of them, it's showing that it is significant, but it actually wasn't, because that p-value, remember, is showing us that there might be a probability of it happening by chance. So but since there's only a few of those, then there may be false positives in there. So multiple testing the caution is just saying that if we have a bunch of significance tests, we can't necessarily make the assumption that they're all showing the same thing. they could be showing different things. So, excuse me. So if it's showing different things, we can't make that assumption in the end that what we find in the end is the same as all the other ones that we found. So does that make sense? So yeah, just think about if you were to conduct a bunch of significance tests and then overall you find that that they're all significant, or that most of them are significant. That's the conclusion you make. But some of them that were deemed significant may have happened by chance, because you are going to have that p-value, the probability that it did happen by chance. You can't assume that all of them were correct. So since there is that probability of it happening, you want to keep in mind that there can be false positives in there, and it's unlikely that all of them were showing significance there. So just that they could be showing differences when they're not different. Does that make sense? Okay. All right, so once again, as always, for the last time, you guys can check out the videos on YouTube to review this one, and then also, the videos from all the other weeks for the other chapters. So, if you were going through this, you're like, oh, I really need to review that one section, go ahead back. All the different videos are labeled, so you can go back and check those out. I think everyone gave me their Penn State email, so thank you so much for that. If you have any other questions for me, please type those in the chat box. If not, you guys are great to go for tonight, and good luck on your final. I know you do amazing because you guys are very smart, so yeah. Yeah, of course.